Hey, hello guys, welcome, vanakkam, vandanam, namaskaram. Today we are going to see solutions part 2. So already we have discussed part 1. So in part 1 till ideal, non-ideal solutions we have discussed, and also here coming to this part 1 itself, I have not explained that clearly normality. So we will start from normality, then I will be giving you a very short recap about Rolle's law. Then we will be going to ideal, non-ideal solutions. Okay, so that there will be a bridge between part 1 and the part 2. Okay, so normality. Okay, maybe already you guys would have studied this in your class 11th itself, or I don't know, have you guys studied this in your class 9th or not, but there are probabilities that you guys could have studied this in your class 9th also. Okay, there is normality, there is formality, already I've said in part 1, right? Okay. So, the formula for normality actually is number of moles of solute whole divided by n factor into volume of the solution. Okay, into volume of the solution. Or wait, I'll give you another formula. You don't use this one. See, there are totally 3 different steps. Okay, there are totally 3. Yeah. So totally there are not 3, 4 different steps. Okay, 4 different steps. The last step is where you are going to get your normality. Okay, the first step is to find your molar mass. Is to find your molar mass. What is your molar mass? Molar mass is the mass that is given by the compounds. The compound formulas you have, right? For an example, okay, so for an example, when you take HCl, okay, when you take HCl, just as an example I'm going to give you HCl, then for hydrogen it is going to be 1, and for chlorine it is going to be 35.5. So it is going to be 36.5 as its molar mass. Okay, so what is this molar mass? Okay, what is this molar mass? First we will come to mole concept. Okay, I said I will make a separate video in the last video, but nope, not that much in deep I'm going to go. We will stop it on the surface itself. See, you have to know 2 different things: relative mass and then molar mass. Relative mass and then molar mass. What is relative mass? Relative mass is actually a smaller unit, okay, a smaller unit than molar mass. That means, for an example, one atom, okay, one atom of carbon is 12 AMU, okay, where AMU is your SI unit of your relative mass. Okay, so for your hydrogen, it is going to be 1 AMU. For your nitrogen, it's going to be 14 AMU. Okay, like that. This will be differing. Okay, this will be differing. For an example, chlorine. Okay, chlorine, it is going to be 35.5 AMU. Okay, but the thing is, AMU is very, very small because it is mass of one atom. And just imagine, there is no way that we can touch or we can feel or we can do chemistry by using one atom. Okay, it's impossible, right? Because even when you take this small cross section, or you just take this one small dot, it will be having millions of atoms inside it. Okay, it will be having millions of atoms inside it. Paramanu will be there a lot. Okay, so you cannot do anything by using this relative mass. What you have to use is you have to use molar mass in this case. Okay. So how will you use molar mass? Very simple. What people have done is they have taken, instead of 12 AMU, instead of 12 AMU or 1 AMU or 14 AMU or 35.5 AMU, they have taken 12 grams. Okay, 12 grams of carbon. 12 grams of carbon. Okay. Okay. Then also instead of 1 AMU, they have taken 1 gram. 1 gram of hydrogen. Actually, what they have done is they have first taken only carbon. Okay, only they have taken carbon. Inside, in that carbon also there are many isotopes, right? In that carbon 12. Okay, carbon 12 is what they have taken. That means in carbon 12 they have taken 12 grams of carbon 12. Okay, and what they did is they have estimated the value. How many atoms are going to be there? Okay, like that they did some calculations and they found that it is going to be Avogadro's number. Okay, they found that it is Avogadro's number, which is 6.023 into 10 to the power of 23. Okay, so that means in 12 grams of carbon 12 isotope there are totally 6.2023 into 10 to the power of 23 atoms. So same applies to other atoms also. That means in 1 gram, okay, in 1 gram of hydrogen, totally there are 6.023 into 10 to the power of 23 atoms. Okay, so from this itself you can see that hydrogen is the least weighted. Okay, hydrogen is the least weighted one. Then yeah, that's it. And do you know why they have specifically taken carbon 12 as the thing? Okay, primarily, even if you see the definition of 1 mole, it will be having carbon 12 only. Because when you take 12 grams of carbon 12 isotope, it will have very less number of impurities. Okay, it will have very less number of impurities. One thing I have to say, I will explain this impurities concept a little bit detail in F and D block elements also, but before that I have to say to you about interstitial compounds. Okay, interstitial compounds, where impurities, in sense there will be interstitial compounds formed. Interstitial compounds. Interstitial compounds, in sense, for an example, you take atoms. Okay, this is one atom of carbon, this is another atom of carbon, this is another atom of carbon. Okay, now you can see that between these there is a space, right? There is a space. In this space there is a possibility of accommodation of different atoms also, like atoms like Na plus, wait, not Na plus, like hydrogen, carbon and nitrogen. Okay, like hydrogen, carbon and nitrogen, these are the 3 primary elements that can go and sit in this place. Okay, so this automatically makes what? This particular element as impure. Okay, this particular element as impure, but element should be very pure, then only that calculation will be very accurate. But since it makes this complete element itself as impure, as I said, right, in this space any of these 3 elements can be there and they can just accommodate. So that, for an example I will take it as sodium. Okay, so in 11 grams of sodium, okay, I will take 11 grams of sodium, 23 grams of sodium, sorry, 23 grams of sodium. Okay, in 23 grams of sodium, there is no guarantee that in this 23 grams of sodium only sodium is there. Also there can be some other compounds like this. Okay, there can be some other culprits like hydrogen, carbon and nitrogen. Okay, so in order to be very accurate, what scientists have found is that these impurities are very less in carbon 12 isotope. Impurities like this, okay, hydrogen, carbon, nitrogen is very, very less. And this is what we will say as interstitial compounds. And also there is some effects, okay, these will not just increase the mass, okay, these will not just increase the count, they will not just increase the count, density they will be making some role, okay, this is said as Schottky effect, okay, like that there are some effects. I will say all of this very clearly in F and D block elements, but now since I have to explain this a little bit, I'll say this. Okay, so that is the primary reason why they have chosen carbon 12 isotope. Okay, so now what we are going to do is, now we will come to normality. What is normality? As I said that there are totally 4 primary steps that you have to do. Okay, so the first step is going to be, first is to find the molar mass. So I will take H2SO4. Wait, I'll first write the question, then we will go. Okay, so what you have to do is you have to find the normality of, okay, so 4 grams of H2SO4 in 500 ml of water. So first I will say to you how to calculate this one, then in a separate video if I can, then I will tell to you what is normality, or shall we see it now itself? We shall see it now itself. Okay. See, the first 4 steps I will write first. Okay, first 4 steps. So the first step is actually to find the molar mass. Okay, so first step is this one. Then your second step is actually to find equivalence mass. Okay, then your third step is to find number of equivalent mass. Okay, then sorry, gram equivalent mass, number of gram equivalents, number of gram equivalents, not mass, just number of gram equivalents. Then your fourth step is what? To find the normality. Normality. Okay, so how will you find molar mass? First, molar mass is actually given in the question itself. Given in the question itself, see it is H2SO4, right? That's it. They have given you H2SO4. So first you have to find the molar mass of H2SO4. Okay, so and see molar mass of solute. So molar mass of solute in sense this H2SO4 is the solute, and then your water is going to be solvent. As we all know that solvent will be always high in quantity. Okay, so H2SO4's molar mass, how will you calculate? Very simple. 2 into 1 for hydrogen plus for sulfur. It is what? It is 35. Not 35. Wait. Oh god, I forgot sulfur. Hydrogen. Yeah, so sulfur 16. So 16, then it is 32. Okay, so 32 plus oxygen ka 16. So 16 into 4. So at last you are going to get 98. Actually, I remember the value of H2SO4 very good. Okay, so you are going to get your molar mass as 98. I forgot for sulfur. Okay. Next is equivalence mass. How will you calculate equivalence mass? Equivalence mass is molar mass. Okay, it is molar mass. Is molar mass divided by n factor. Okay, divided by n factor. Then, in that sense, how it is going to be? What is your molar mass? Molar mass is 98 grams. Whole divided by n factor. See, for H2SO4, there are totally 2 different possibilities. Your n factor can be either 1. Okay, your n factor can be either 1, or also your n factor can be 2. Okay, this is or either or possibilities. For H2SO4 it is one common example. Okay, I explained to you in the previous video itself. Okay, so let me assume it to be 1. Okay, I will explain why what is 1 and what is 2. If in case it is 1 now, then the value is going to be 98 only. Okay, so your equivalent mass is going to be 98. If in case it is 2, then it is going to be 49 grams. Okay, here it is grams. That means what? Actually, what does this number mean? What does equivalence mass mean? It means that out of 98 grams, okay, out of, where is this? So molar mass of H2SO4. H2SO4 is 98 grams. So out of this 98 grams of H2SO4, when n factor is 1, 98 grams of H2SO4 can react. Okay, that means every part of this H2SO4 can react. But when n factor is 2, that means only 49 grams can react. Okay, that means only 49 grams can react. Out of this total 98 grams, only 49 grams has the ability to react. So then that's it. Okay, next is number of gram equivalents. So here it is equivalence mass. Here how many numbers of gram equivalents is there? That is what we are going to find. So how we are going to find that? It is going to be given mass. Given mass is what they are given in the question. Okay, so given mass. So that means what? What does this mean? Okay, by equivalence mass. Now you are going to find how, like this. Okay, see here, how can I explain this? See, out of 4 grams, okay, out of 4 grams, since given mass is 4 grams, out of 4 grams, how many grams of H2SO4 can react? Out of 4 grams, how many mass or how many grams of H2SO4 can react? That is what this number of gram equivalents mean. Okay, that means out of 4 grams of H2SO4, how many grams of H2SO4 can react? Okay, so it is going to be 4 grams divided by, okay, so if n factor is 2, then it is going to be 49 grams. Okay, so the value has been already calculated by me, which is 0.0816. Which is 0.0816. Now, how will you calculate normality? How will you calculate normality? Very simple. All you have to do is put this value here. Okay, put this value here. So that means it is going to be 0.0816 whole divided by. Okay, so 0.0816 whole divided by. I'm rotating. Great. So 0.0816 whole divided by volume. Okay, volume of the solution in liters. Okay, so that means that is not correct spelling, I know. Okay, so 0.0816 whole divided by. So in terms of liters, okay, in terms of liters. So in terms of liters, that means volume. What is the, see, volume is 500 ml of water, right? So here just add 500 ml like that itself. So 500 into 10 to the power of minus, or you can write it as 1 by 2. 1 by 2. 1 by 2 liter is more comfortable than writing 500 into 10 to the power of minus 3. So which is equal to. So I just double this value. So double this value, now then you will be getting. No, I have not calculated that one. So then just double of this value is going to be. I'm not going to multiply this, just double it. So then it is. Okay, so it is going to be 0.1632. Okay, it is going to be 0.1632. Oh god, I'm very slow. Okay, so that means when you're doubling this, it is going to be 0.1632 as its normality. Okay, so this is how we are going to calculate your normality. First you have to find the molar mass. Okay, then you have to do what? Then you have to divide that molar mass by n factor. Then you will be getting your equivalence mass. Then you have to calculate how much number of equivalence mass is there. okay, in the given mass, okay, in the given mass. So how will you do? So just take that given mass and then divide this value with that one. So that means 4 by this one, okay, 4 by this calculated value. So which is going to give you this 0.0816. Now just give that value as input. Okay. So that means how can you write this? Okay, how can you write this? Given mass, the first step is what? Given mass by what? Okay, by number of gram equivalence weight, right? So for number of gram equivalence weight, when we, okay, so for number of gram equivalence weight, see, for normality it is going to be number of gram equivalence weight, number of gram equivalence weight divided by volume. Okay, so for this one, given mass by equivalence weight, whole divided by volume. Okay, so that means for equivalence weight, what it is going to be? It is going to be molar mass divided by X, correct, right? So given mass whole divided by molar mass whole divided by, that means for this like this, then for this n factor, then whole divided by volume. Okay, for equivalence weight correct, or equivalence mass it is actually, yeah, correct, molar mass by correct. So how can you write this? One second. So this okay, so you can just do it like given mass. Okay, so you can write it as given mass into n factor whole divided by molar mass. By the way, given mass by molar mass is what? Okay, given mass by molar mass is what? Given mass by molar mass is your moles. Okay, is your moles. So that means you can write it as moles into n factor. Okay, as moles into n factor whole divided by volume of solution. Correct, right? So volume of solution. This is moles of solute. Okay, moles of what? It is moles of your solute. Now, what is this? Okay, moles divided by volume of the solute. Okay, this one is what molarity is. There is molarity. This is no, not this one. Yeah, here you are. Okay, see, number of moles of solute divided by volume of solution. Where are you now? So actually your normality formula is this one. Okay, so that means normality is this one formula, which is number of moles of solute into n factor whole divided by volume of the solution. Okay, whole divided by volume of the solution. Then now your molarity is what? Your molarity is this one. This is what the shaded area is, what your molarity is. So molarity into, so that means this molarity into n factor is equal to your normality. Molarity, okay. So your molarity into your n factor is equal to normality. Okay, just remember this, that is moles into n factor by volume of the solution. Moles into, okay, or you need not even remember this, just remember this one equation, normality. Just what is normality? Moles divided by volume, okay, multiplied with n factor. That's it, you will get it, you will get the normality. So you need not even remember the formula of normality, because if you remember already the formula of molarity, the formula of normality is going to be very easy. Okay, so molarity is more likely what is actually, I'll give you a little bit hint. Okay, molarity is actually you are finding the concentration, the total concentration of solute with respect to the solution, whereas in the case of normality you are finding the concentration of the reacting amount. Okay, in that total amount, how much amount can be reacted. Okay, in this total amount of 4 grams of H2SO4, how much amount of H2SO4 can react with respect to the total solution. It is also concentration only, but it is the concentration, it is a specific concentration. Okay, actually your molarity is a type of normality. Okay, your molarity is a type of normality, or you can say as vice versa. There is no such sentence like that. I have not heard it, but it is like that only. Okay, here you are just calculating the concentration of the reacting part of the solute. Okay, that's it. This is what your normality is. Now coming to Rolle's law itself. Rolle's law. Where is it? So, what is Raoult's law? Raoult's law is saying that the total pressure that is created by the solution is equal to the pressure that is created by its constituent components with their mole fraction. Yes, right? Okay, the vapor pressure of a solution is related or is totally created. What I said is my English, here it is the theoretical English, which is vapor pressure of a solution is related to the vapor pressure of each component and their mole fraction in the solution. Okay, so yeah, of each component. Okay, so the vapor pressure of the solution is equal to the vapor pressure of each component and along with their mole fraction of the solution. Okay, so here I've given you, also I said you that Raoult's law is a special case of Henry's law, and KH is equal to P naught A, and also KH is equal to P naught B. All these I said to you, okay, in the last video. Okay, now what we are going to discuss is ideal and non-ideal solutions. What are ideal solutions and what are non-ideal solutions? Solutions, also I did not say what is polar solutions and non-polar solutions. Okay, polar solutions and then non-polar solutions. See, polar solution is where that solution can be split into its constituent ions. Okay, a solution which can be splitted into its constituent ions. Best example, electrolytes. Electrolytes can be given as an example. Okay, then ionic solutions. Okay, I will just check one time. Yeah, correct. Then acids, strong acids, or acids and bases will be coming in electrolyte itself. Right? Then what is the problem? Okay, non-polar solutions are those which can, okay, a solution which could not be or which cannot be split into its constituent ions. Okay, which can't, okay, which cannot be, okay, which can't be split into its constituent ions. Examples are organic acids or organic substances, not acids, substances. Okay, or organic solvents. Sorry, here organic solvents. Okay, organic solvents are the examples. Like CH3CO, CH3, correct? Correct. Okay, benzene, acetone, benzene, C6H6, then acetone, and etc. Okay, and one more thing, that is a polar solvent, a polar solute will be dissolving in a polar solvent only, and a non-polar solute will be dissolving in a non-polar solvent only, and that is the reason why water is not dissolved into oil. So because oil is non-polar and water is polar. Yeah, water is also an example. H2. here oil. Okay, the oil that we use, right? That is why oil cannot be dissolved in water, or the vice versa. That is why even in pasta we use oil while boiling, so that pasta will not be sticking to each other. Perfect. Now coming back to solutions itself. See, a solution is actually of ideal solution and then non-ideal solution. See, it will be an ideal solution when it follows Raoult's law. And it will be a non-ideal solution when it does not follow Raoult's law. Is not followed. Okay, so what is Raoult's law? P naught A of XA plus P naught B of XB is equal to P total or P net. Okay, then what about non-ideal solution? For a non-ideal solution, see, here it is equality, right? So this is equal. In that case, it is ideal solution. But when it is not equal, it becomes non-ideal solution. Okay, see, here it is equal. Here it is equal. Hence, it is ideal solution. But here it is a non-ideal solution because here it is not equal. Not equal. Ideal not equal. Okay, so here it is equality. Here you use equality. Then what will you be using here? You will be using here inequality, less than or greater than. Okay, less than or greater than, mathematics class 11 standard. I don't know which chapter it is, but inequality. Okay, so which means I can split it like this. Okay, why to be such a conjugational space? So what can I do? Okay, that means P naught A XA plus P naught B XB is actually greater than P net. Okay, this is a condition that you can say. The vice versa is also okay. The vice versa is also okay. So that means, okay, so flip. So here you can see that these are inequality, and whenever you are having something like this, it is known as positive deviation. Okay, this condition is known as what? It is known as positive deviation. Okay, I'll explain this later. Now I will explain. Okay, so this is ideal, this is for non-ideal solutions. Okay, there are also still some other conditions that I have to say, and some examples are there that I have to say. First is delta V mix is equal to 0, and also delta H mix is also equal to 0. What does this mean? It means that volume. Okay, delta V mix now it is volume. Well, when you are having, okay, see, that means what is this? This is V2 minus V1, right? So you are having water. Okay, let me take water. You are having around 250 ml of water. Okay, now what you are doing is you are adding a solute to it. Okay, this is solvent, you are adding a solute to it in addition. Okay, now there should be no change in the volume, even though you have added some amount of solute to it, but there should be actually no change in the volume. That is what this first condition is. Okay, next is no change in the enthalpy. This is more likely to be a thermodynamical concept, so you have to know what is thermodynamics, and I have not yet put any videos for thermodynamics. Don't worry, I will start to put videos as soon as possible for thermodynamics, for equilibrium in chemistry, and as well as for organic chemistry of class 11 standard. In physics, we will start to make motion in 1D, motion in 2D dimension videos also. Okay, so come back to here itself, where dH means what? That means the energy, okay, the energy before adding solute. The energy that is before adding solute should be equal to the energy that is after adding to the solute. So what does this mean? Actually, this condition can be also written as V2 minus V1 is equal to 0. Okay, this is what this condition, which is delta V is. So which can be reinterpreted as V2 should be equal to V1. Okay, just bring that to this side. Okay, and here also the same thing, which is H2 is equal to H1. Okay, so these two are important conditions. Now, other than this, do I have something else? Yeah, examples we have to see. Okay, examples we have to see. What are the examples that I can give you? Well, N-heptane is there, N-hexane is there, N-hexane, then N-heptane is also there. Okay, N-heptane, N-hexane is there, then bromoethane is there. Then chloroethane is there. Okay, then benzene is there. Okay, then toluene is there. Now, what are they? N-hexane, N-heptane, bromoethane, chloroethane, benzene, toluene. Okay, so that means N compounds are there and ene compounds are also there. N compounds and then ene compounds both are there. Well, like that you cannot keep it blendedly, because here also there can be N and ene. Okay, so you have to remember this. How can you write this? N hexane or heptane. Okay, then bromo or chloroethane. Okay, yeah, chloroethane. Then benzene and then toluene. Toluene, how many of you guys know what is toluene? If you don't know, don't worry. In organic chemistry, I will say it is actually another name only. Okay, even I forgot. Okay, but I remember that I have read this word in organic chemistry. Okay, so toluene. Okay, so these are there. Again, that is what I am writing, but instead of writing like this, you can write it as N-hexaheptane, then bromoethane, chloroethane. That is what, like haloethanes. Okay, like that you can write it as. Then benzene and toluene. Okay, these are for ideal solutions. That means no matter how much solute you add, the delta V mix and delta H mix will be the same. Okay, next is coming to the case of non-ideal solutions. So as I said that you are having, oh come on, okay, so you are having two different cases. I have done this very big. Okay, so what are they? They are actually ideal, non-ideal, na? So non-ideal right. Non-ideal solutions. Right. Okay. See here, in case of In case of non-ideal, what did I say? You are having P naught of A into XA plus P naught of B into XB is equal to P net. Sorry. Case greater than, and another case is okay. So another case is this one. So which means what? Now we will dive into the concept. Okay, we will dive into the concept still more a little bit in deep. See, you are having okay. Okay. So first is we will be discussing in this one. Okay, this concepts we will be discussing. Okay, so first concept is actually this one. So this particular thing is there, right? This is also known as negative deviation. And in this one is it as positive deviation. I also say wait, positive deviation. Okay, so coming to the case first, negative deviation, I said first. So what does this mean? See, you are having actually AA bond, then BB bond, then AB bond. Wait. Okay, I don't know what's my problem with this thing. Okay, now it's kind of good. So actually these are this one. Okay, AA bond and BB bond are these things only. Okay. So this is AA bond. So in order to break this bond, you want some amount of energy, right? You want some amount of energy. Let us keep that EA. Okay. There is also another EA in chemical kinetics. Do not get confused. Okay, that is initial. I am getting that name confused. Initial energy. No. Okay, we will see there itself. Then it is EB bond. Okay, this is EB. Then it is EAB. Okay, it is EAB. So in order to break this, you want A amount of energy. Then in order to break this, you want EB this much amount of energy. In order to break this also, you want this much amount of energy. Yes, right? Okay. So now what I'm going to do is, or what I'm going to say is negative deviation, right? Okay. So the energy, okay, the energy that is required to break this, okay, this EAB is greater than the sum of energy of E and AB. Okay, so that means like this. Okay, the energy that is required to break the bond of EB, that is required to break the bond between that is required to break the bond between A and B is greater than the sum of energy that is required to break the bond between A itself and B itself. Okay, so okay, so that means what? That means since this energy is actually a lot of energy is required, okay, a lot of energy is required, and here the energy is going to be heat energy. Okay, that energy is what? Heat energy. So that means what? That means you want a lot of heat energy in order to break this bond, but comparatively you want only less energy to break this bond and this bond. Okay, like this one you can take, or you can also take separately. Okay, separately also you can take, or also some also you can take. We will take separately itself. Okay, separately itself. So that means this energy is more than the energy that is to break AA bond or to break BP bond. Here I have used the word or. Okay, so I will put there also or and under different. And then I have to do some, or no, you should not do some. You have to take either of the one cases. Okay, so come back to here itself. So that means here this energy is there, right? So which means that PA, okay, PAB, the pressure that is created by AB is going to be lesser than the pressure that is going to be created by PA and then PP. Yes, right? P naught A, P naught B. Because it is in their very own form. So whenever it is in their very own form, or whenever it is in their purest form, you have to put naught. Okay. So that means I can write it as P naught A plus P naught B is greater than PA plus PP. Okay. So here, 1 second. Yeah, correct. This one is how it is going to be. Okay, so which means what? This is what P net. Okay, as I said that already, this is what P net is. But the thing is, I have not yet included here the mole fraction. You can also include here mole fraction. That's it. Okay, very clear. I hope it is all. Now you take the exact same thing, but the thing is, this time you have to take energies in different. Okay, this time you take this energy is greater. Okay, that means in order to break this AB bond, you want to give only less amount of heat energy itself. So let's take a particular temperature. Let it be 298 Kelvin. Okay, 298 Kelvin. So since that means 25 degrees Celsius. 25 degrees Celsius. Okay, so you want 25 degrees Celsius or this much amount of heat in order to break this bond. Okay, in that time there will be particular amount of pressure. Okay, that will be created. Let us keep that it is PA plus PP. Okay, and if you give the same amount of pressure, okay, since this bond is very strong, okay, than this bond, so that means less amount of pressure only here it will be produced. Yes, right. So that it is going to be P naught A and then P naught B, which is going to be like this. Okay, which is going to be like this, because with less heat itself you can create more pressure in the solution, but in case of solute and solvent you want to apply more heat. Okay, but you have to give equal amount of heat. When you are giving equal amount of heat, then this is what your condition is going to be. So you can also multiply it with your mole fraction in here. So it is going to be XA and here it is XP. Okay, so this is what your negative, here it is going to be positive deviation, here it is going to be negative deviation, or here I can write it as like this. Okay, PAB I have written or PAB I have written, you can write like this also. See, why to have any confusion here alone, you will write it as PA plus PP. Okay, PA plus PP. Okay. Now, coming here itself, we have some examples. Okay, for negative deviations you have some examples, and then for positive deviations also you have some examples. For the case of negative deviation, what are the examples that you are going to have is not that much you are having, or not that much they have given. These are some examples. That is going to be chloroform plus acetone. Okay, so no, here if I'm writing now, it will not be correct. No space, no space, no space. For this I will write here. Okay, so that means for positive deviation, examples are going to be acetone. Wait, yeah. So ROH plus H2O H2O is going to be a common example in this and this, so note this. Okay, what is this ROH? R means what? It is it is like alcohol. Okay, alcohol plus water. So alcohol plus water will be always giving you what? It will be always giving you positive deviation only. Okay, so this is alcohol plus water. OH na alcohol, ol. Okay, so then after that you are also having alcohol. Okay, alcohol, water, or also you can use here cyclohexane. Cyclohexane. Okay, then or else you can also use acetone plus hexane. Okay, acetone plus hexane. Acetone will be coming here twice. In positive deviation, acetone will be coming here twice, but in negative deviation will be coming only once. Okay, so acetone plus hexane is also an example. Then carbon disulfide, which is CS2. CS2 plus acetone. Okay, so instead of hexane also you can add carbon disulfide, which is going to be CS2 only, CS2. Okay, see, in place of hexane you can I can put the formula also, like in that case it is going to be C6H14. Okay, C6 it is going to be H14, C6H14. In case of cyclohexane it is going to be C6H12. Okay, this is what the formula is, but I have written there like this itself. But in case in examination hall they have given in terms of formula, then please don't get confused. Okay, and I have not yet uploaded nomenclature. That means we have not even touched a part of organic chemistry. We are still in physical chemistry itself. First 3 lessons of class 12 is physical chemistry, for solutions, electrochemistry, then last but not the least, that is chemical kinetics. Okay, those 3 are actually physical chemistry. Then you are having inorganic chemistry, which is F&D block, and then coordinate chemistry. Then at last we are having 4 bada chapters, which are no, I have not yet started those in my school, or neither I have not yet done own preparation. Well, some I know. Biomolecules we have. Then haloalkanes, do we have? I think so. We have. I read that like that we are having 4 or 3 chapters. Those all are organic chemistry. And other than that, 11th organic chemistry also we have to touch. We have not yet put any one video. And 11th is very important. And 11th is very easy than 12th. Believe me, 11th is very easy. Okay. Thermodynamics and equilibrium only here and there it will be like that. But other than that, 11th is very easy than 12th. Okay. So coming back to the next here itself, which is going to be ethanol. Also, where is this whole ethanol? Along with ethanol, I can also add acetone. Did I write here acetone? Acetone. Wait, why to be this much Hanjapisnari with space? Why to be such a cheapsteak with space? Okay, so I'll write here. So positive deviation. Positive. Yeah, we have to also discuss graph now. Okay, deviation and then negative deviation. Okay, and also we have to discuss the graph of ideal solutions. Okay, so this one's examples are going to be, as I said, that alcohol plus water. Okay, so alcohol plus water, or else also alcohol plus acetone. Okay, then cyclohexane, then hexane. Okay, so cyclohexane and then hexane. What you can do? Cyclohexane and then hexane. This is to acetone. This is to acetone. Acetone, and then the cyclohexane is to again ROH. ROH. Okay, then you are having acetone again. Okay, acetone plus carbon disulfide. Then you are having ethanol plus acetone. See, remembering everything like this is kind of tough. Okay, so what we are going to do is we are going to short it down. Okay, see, alcohol. Okay, so where all you are having alcohol? Alcohol, 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 and then ethanol is also there. So these three are what? These three are actually types of alcohols only. So see, this is also alcohol, this is also alcohol. Here also acetone is there, here also acetone is there. So that means you can remember whenever acetone is added with alcohol, it is going to show you positive deviation only. Okay, so this one you can erase, and then in place of this one, okay, so whenever you are adding alcohol along with water, it is going to show you positive deviation, or alcohol along with acetone, it is going to show you positive deviation, or also cyclohexane. Okay, cyclohexane, it is going to show you positive deviation only. So that means I can erase this, and then I can erase this. Now come to acetone. Acetone will be showing positive deviation along with alcohol, then along with carbon disulfide, then also along with hexane. Okay, now it is going to be a little bit easier. Okay, now it is going to be a little bit easier. How will you remember this? Alcohol nale. Okay, if you hear the word alcohol, what has come to your, what other element or what other compound? Okay, what other compound comes to your brain? Water, right? So alcohol, when you are adding alcohol with water, it is going to show you positive deviation. Okay, and in water, what will be there? C is there, na? So actually, C is filled with C is water. Yes, right. C is made up of water, and in C, what you will be having? You will be having cyclones. Okay, cyclones. So that there will be an agitation, which is acetone. Okay, so you can remember it like this. Just now I have created this mnemonics. Just now, and this one is already here. Okay, this one is already here. Now you can remember it like this. Agitation. Okay, agitation is happening. CS. Okay, for me personally, I don't like computer science at all. Not even a bit. I'm allergic to the subject. Every time I open that book, okay, I had IT in my class 10th and in my class 9th, and every time I open that book, I will be getting head pain because I cannot understand anything. Oh, what is this? I could not understand anything. So you are having agitation with CS2, then also with hexane. Well, with hexane you have to remember this. I cannot find anything. Or hesitant. I'm hesitant to learn something. Okay, in CS I'm hesitant to learn something, so that I'm getting agitation. Okay. Okay, so this is how you are going to remember this. Now coming to negative deviation. See, you have to create pathways for your neurons, to connect with each and everything, and the connection of neurons is what going to give you memory. Where is this? Okay, is what going to give you memory. So as much as you revise, that much connections will be again and again made, so that your brain can know that it is a very easy thing. Okay, so I know nothing made sense that I said. I will say in one of the shots. So next example. What is your next example? Is actually for negative deviation. You are going to deal with chloroform plus acetone. Okay, acetone. Chloroform plus acetone. Then other than this, if you want something not, then strong acids like HCl and then HNO3, not NHO3. Oh, sorry. H and nitric acid, HNO3. When it is added to water, then it will be showing negative deviation. But when alcohol is added to water, then it will be showing you positive deviation. Okay, this is one example. Then one more example is that. So trichloromethyl. No, it's not going to be like that. But this is actually, this particular compound is formed by continuous reaction. See, reaction is actually of three different types. One is continuous reaction, then next is parallel reaction, then another one is opposing reaction. In chemical kinetics, I will be saying to you all, so amongst this, this one is formed by continuous reaction. I will check that. Yeah, sorry, consecutive reaction, not continuous, consecutive reaction. Okay, so when you add to this compound, okay, so yeah, I've given you every example. By the way, the structure of acetone is going to be like this: CH3, CH3, then one bond, then one carbon, then double bond oxygen. Okay, correct. Okay, and as I said, the chloroform is going to be CH. Hey, this is what that compound is: CHCl3. Okay, chloroform is going to be CHCl3. I don't know. Brain is not working again. Okay, so CHCl3. How you are going to name it? Okay, how you are going to name it? See, this compound structure is what you have seen there. I've already drawn there. That is CH. Okay, Cl. Okay, this is how the structure of the compound is going to be. Now you can see that there are totally three substituents. So you have to write all these substituents first in the nomenclature. Since there are three, so trichloro. Okay, how many carbon? Only one carbon, right? So meth. Okay, so meth. Then how many bonds are there? Only one single bond, so ene. Okay, so trichloromethane. Okay, so this is what the structure of acetone is. Acetone, so wait. Acetone plus CHCl. Okay, so when you add it, then you will be getting a negative deviation. How will you remember this? Very simple. Acetone is everywhere, pa. Acetone is everywhere. This one I said to you. But here I have got one more thing, that is, what is chloroform? Chloroform is trichloromethane, right? So tri means what? It's kind of similar to the word trident. Trident, which is with God. Okay, in Hinduism, Lord Shiva uses it. When will he use it? Whenever a negative incident happens, he will be using it, right? So negative deviation, then trident will be used, which is trichloroethane along with acetone. Okay. Here you are having water. Okay, Jalandhar, who is a son of Lord Shiva, the negative part of Lord Shiva. Okay. Now we will not go to there at all. Now we will come back to here itself. The graph. Okay. x1, x2, then again x1, x2. Here I am going to assume x1 as 0, here I am going to assume it as 1, here I am going to assume it as 1. Wait. Okay, well, like this to be assumed, or shall I assume it in the usual way? Yeah, I will assume it in the usual way. One, 0, 0, 1. Okay. Now, what happens is this is one. Okay. Imagine that this is the concentration. Okay, so the mole fraction. So not the concentration, the mole fraction. Okay, anyways, both are same only. So mole fraction of mole fraction of solvent is 1. And here the mole fraction of solute is here 1. That means here you are having what? Here you are having only a beaker that is completely filled with solute, and here you are having a beaker that is completely filled with solvent. Okay, completely filled with the solute and then completely filled with the solvent. Now what you are doing is, here you are actually going to give heat. So then automatically there will be P naught. Okay, P naught, instead of keeping this as 2, I will keep this as B. Okay, so B. A. And then A. Okay, so that means this is going to give you a pressure of P not B. Okay, and then this is going to give you what, when you are giving heat, this is going to give you a pressure of P not A. Okay, now what you are doing is here what you are having is you are having solution. Okay, you are having a solution. Well, in our book this line is a little bit slanting. They have not drawn this like this, they have drawn it like this. So that means one is going to be volatile, another is going to be non-volatile. Well, non-volatile nature is a little bit less. That means one's volatile nature is higher than the another's volatile nature. So that means I can assume, what shall I assume this? So I will take this one's volatile nature to be higher. Okay, so I hope that is all clear. I will check whether for which one they have taken high. For the solution that shows positive deviation, yeah, for this they have taken like this. Yeah, for both of them, A is what? More volatile. Okay, A is what? More volatile. Because here it is solvent now. So solvent will be more volatile than the solute. Okay. Now what you're doing is, this center part is the solution. Okay, the center part is the solution. That means you are mixing this and mixing this. Okay, so that means this A will be mixed to, okay, sorry, this B will be mixed to A. Yes, right? Okay, so automatically you are going to get this one's pressure like this. Okay, this one's pressure like this. Why are you getting it like that? It is because, wait. This is actually for, I'm explaining for non-ideal. First you will see for ideal. What I'm saying now is for, actually for ideal. Okay, so for the case of pressure, ideal solution of constant. Yeah, so for the case of ideal, what they have done is they have taken P not B. That means this is what? Solute. So ideal, so positive deviation. For this one, what they have done is they have taken this one to be more greater. So yeah, first I have to explain ideal, then only you will be getting it. You will be getting the idea. Again, there is no space. Okay, so in the case of ideal solutions, okay, so in the case of ideal solutions, we have graphs, right? See, first I will explain this one. Same, which is P naught A and then P naught B. Wait, oh, what am I writing? XA, XB. Okay, then here also XA, XB. Here it is going to be 1, here it is going to be 0, here it is going to be 0, here it is going to be 1. Okay. So that means here only I am having solute. Here I am having solvent. Okay, then if I give here heat and if I give here heat, okay, automatically this XA will be converted into P naught A. Okay, this XB will be converted into P naught B. Why so? Why is there such sort of difference? It is because you all know, right? when I boil this XA, automatically this XA will be giving you some sort of pressure, and since it is in the purest form, which will be P naught A, and same thing applies to XB, which is going to be P naught B. So when I draw the graph is going to be like this. I'll choose white color so that it will be more dominant. Okay, so this is going to be like this. And my question is, why is it going like this? Okay, and why here it is going like this? Okay, see here it is just pure what is this? Here you are having just solute, here you are having solvent. Sorry, here you are having just solvent, here you are having solute. Here it should be solute, right? Solute. Fire this is, and here it is going to be solvent. Okay, this is also fire and B. So this is going to increase, this is also going to increase. See, XA is there, right? Here XB is actually 0. So that means what? That means PB, okay, P naught B is also 0. P naught B is also 0. Here A, okay, here P naught A is also 0. Here P naught A is also 0, right? Okay, so P naught B is 0. Here P naught A is also 0. So these two are 0. Next is, see, when you are boiling this P naught B, actually this XB, first it will be like this, okay, first it will be just XB. Now, when you are adding this solvent and solute, here it is going to be just the solution, okay, solution. When you boil a solution, it is going to give you some pressure, right? Okay, that pressure, when you take this pressure, okay, this solution's pressure is going to have PA and then also going to have PB. Yes, right, this is going to have PA and then this is going to have PB. Now when you take, okay, when you take just this XA1, okay, where XA is equal to 1, as you boil this, okay, the pressure will be increasing, and at last the pressure will again start to decrease because this mole fraction, this total fraction, the fraction will not reduce it like this, but the XA amount can be completely gone. Okay, it will be completely gone, because if total amount of XA has got evaporated, then nothing will be there to be evaporated, then it is going to be 0. So you can see that it is going to be 0. Okay, so P naught A is going to be here 0, or PA is going to be here 0. Same thing applies here also. So as you boil XB, which is equal to 1, first in the beginning it will be high, then as the time goes it will be reducing, okay, it will be reducing, and at last you will be having, what am I going? Yeah, XB, so it is going to be PB is equal to 0. Okay, so PB is equal to 0. Okay, now when you talk about the solution, when you talk about the total solution itself, okay, this is what the line for solution is. Well, in our book, they have given a similar diagram, and I have also given you all similar diagram only. Okay, what they have done is they have a little bit tilted it upwards. Okay, tilted it upwards, which means this is more volatile, this is less volatile. Sorry. This is more volatile, this is less volatile, or this is more non-volatile, this is less non-volatile. Okay, now, yeah, this is going to be P of A plus P of B, or yeah, okay, and then this is going to be P of A, and then this is going to be P of B. As it tends to 0, here also tends to 0. Then here this total line, okay, this is what the tending line is. This is what, there is no such name in our chemistry book, I'm just saying with my English. Okay, so this is PA plus PB, that's it. You will come back to here itself. Now what actually happens is, now I will take this one a little bit higher and this one a little bit lesser, because solute will be actually little bit more non-volatile. Okay, so this I will be taking less itself. Okay. First, what you have to do is, first you have to draw the graph for ideal solution. You just draw the graph for ideal solution. Okay, well actually for ideal solution it will be like this, but here you have to draw like this one. Here you have to draw like this one. The same thing you do here also. Okay, so here also same. So this is going to be solvent and then solute. Okay, as the name which is positive deviation, so that means actually why is there this positive deviation? The name has come as what is my English? Okay, so the name positive deviation has arrived because of this graph, mainly because of this graph indeed. Okay, as per this name which is positive deviation, also this graph is going to take a positive deviation. So that means it is going to be like this, and here also it is going to be like this. Okay, and automatically there will be, when you have an increase in this line and this line, automatically there will be an increase in this line also. Okay, when you are having negative deviation, that means this deviation is going to be like this, and then this deviation is going to be like this, then automatically this deviation is also going to be like this. Okay, this deviation, that deviation, and all these deviations. Okay, so solvent, solute, everything is there. Okay, everything is pakka. Now I will start to name. I will name it. So what is this? This is going to be PA line. This is going to be PB line. This is PA plus PB. Well, here it is not the line. This arc is what PA, and here this arc is what PB, and this arc is what PA plus PB. Okay, and the same thing applies here also. This is what going to be. Okay, PB, and then PA, and then PA plus PB. Okay, so that means it is going to be like this, and there it is going to be like this. Then shapes. Okay, that's it. This one we have successfully completed. What did we complete? We have completed positive, negative, all these deviations. Now we have to enter into colligative properties. Okay, very, very, very important. 5-star. Then into abnormal molar mass. Yeah, abnormal molar mass. So colligative property. What is a colligative property? See, a property which does not depend upon the nature of a solution. Okay, so a property which does not depend upon nature of a solution or solvent or solute, but instead it depends on that number of particles. Okay, number of particles of that solution or solute or solvent. Okay, solution you have to take. Do you know why did I smile? I got ice cream. I'll eat and will come.